In this video, we're going to be doing an AP Physics 1 FRQ for Unit 7 oscillations. Let's say we have a block of mass M is attached to an ideal spring of spring constant K on a frictionless horizontal surface. The left end of the spring is attached to a fixed wall and the block is pulled a horizontal distance A to the right of the equilibrium and released from rest. So on the diagram below, we want to draw and label the force that is acting on the block when it is at its displacement position of x is equal to positive A. So at this point, since we are not at equilibrium, we have this spring force that is going to be pulling the block back towards equilibrium. So our only horizontal force is going to be the spring force. F is equal to negative kx. And when we're at x is equal to positive A, we are going to have the displacement of positive A. So this force is going to point to the left. So on the block, we're going to have a force pointing this way. We'll call that Fs. The reason is because our spring force is always going to be opposite from the displacement from equilibrium in direction. Starting with Newton's second law, derive an expression for the acceleration of the block when it is at position x. At position x, we can start with Newton's second law. We are going to be examining the horizontal forces since our vertical forces are going to cancel out because we have no vertical acceleration on our block. We would have normal force and we would have gravity, but that equals to 0. So, analyzing in our horizontal direction, we have our net forces is going to be equal to Fs. So, for Hooke's law, we have that Fs is equal to negative kx. So we set that equal to ma. If we solve for acceleration, we divide both sides by m, and we get that our acceleration is equal to negative k x over m. We can see that acceleration is going to be directly proportional to our displacement, and we can see that with this negative sign, what it means is it's pointing back towards equilibrium. At what position is the speed of the block the greatest? Explain your answer. Well, it's going to be at a max speed when you are at the equilibrium, aka when you're at x is equal to 0 from your displacement. The reason is because when you're at x is equal to plus or minus a, when you're at an amplitude away from the equilibrium, the block momentarily stops before reversing direction. And we know that when we reverse direction, we have a changing velocity from positive to negative. So if this is your velocity time graph, you're going to be passing through 0. So you know that you have a state where v is equal to 0. However, when you're at x is equal to 0, the spring is unstretched. So our potential energy, US equals 1/2 kx squared, is going to be at its minimum. And we know that our energy is going to be conserved because we have no friction here. So our lost potential spring energy becomes kinetic energy. So that means that K max is at x is equal to 0. So to summarize, we know the block moves fastest where all the spring potential energy has converted into kinetic energy, aka when we are unstretched. Derive an expression for the maximum speed of the block in terms of k, m, and a. We can use conservation of energy because we have no friction, no external forces that are going to be doing work to take away energy from the system. So let's start off with doing this for when you're at maximum stretch, x is equal to a. So your kinetic energy initial is equal to 0, and your potential energy initial is equal to 1/2 Ka squared. When you are at your equilibrium, x is equal to 0, your potential energy final is equal to 0, and your kinetic energy final is equal to 1/2 mv max squared. We set our initial equal to our final. So we can cancel out that 1/2. We get that Ka squared is equal to mv max squared. We can divide both sides by m. And now we just take the square root. Vmax is equal to A, you can bring out square root of K over M. So our maximum speed happens where our US has fully converted to kinetic energy. Derive an expression for the period of oscillation. We saw earlier, we saw acceleration is equal to this expression here. So acceleration is equal to negative K over M times X. We also have a simple harmonic motion condition, which this will be because we are going to be oscillating back and forth periodically. Acceleration is equal to negative angular velocity squared times displacement. So if you have omega squared is equal to K over M, we can do that because we have acceleration over there, and this is also equal to acceleration. So basically you just set them equal to each other. You get omega squared is equal to K over M. Then we have omega is equal to root of K over M. We also know that period is related to angular frequency. Period is equal to 2 pi divided by your angular velocity. So you can plug in your angular velocity here. So this becomes 2 pi divided by the root of K over M. So it simplifies to 2 pi divided by M over K, since you have to flip these two because you're moving this entire thing to the numerator. So we can see from this equation that our period is going to be dependent on two variables, on our mass and our spring constant, not on amplitude, which is a question that they usually ask you. What happens if you change the amplitude? If you change how much you pull the spring from displacement, how does that change the period? It doesn't affect it. Only your mass and your spring constant do. The block is replaced by a new block of mass 4m. The spring and amplitude remain the same. Determine how the maximum speed and the period change. Justify your answer. So we know that originally we had that Vmax is equal to our amplitude divided amplitude times K over M. In our new situation, we have M prime, is what we're going to call our variable, is equal to 4m. So then if we calculate our new Vmax, this will be the exact same thing, but you're going to take where you see M and you're going to replace it with 4m instead. So right here is where we replaced it. So here we can see that 4 can be taken out. And we get 1/2 times Vmax is equal to V prime max. The reason why is because you can see that if you take the ratio of this to this, you can see that everything is going to cancel out. A, K over M, this, all of that cancels out except for a factor of 1/2. So that's how we can tell that 1/2 scalar is being multiplied by the original